Hello, everyone. Welcome to the lesson on Principles and Applications of Mechatronic Systems. I'm the lecturer, Leon Guangrui. Today we look at Chapter 4, Servo Control Technology, AC Permanent Magnet Synchronous Servo Motor. Servo motor is an important core component in industrial automation, which plays a key role in promoting the development of the whole industrial production. We have three main learning objectives in this lesson. First, understand the development evolution of servo motors from DC to AC and its technological breakthroughs. The second is to master the composition, working principle, and FOC control technology of AC permanent magnet synchronous servo motor. The third is to understand the advantages, application fields, and market status of servo motors. Let's first look at the overview of servo motors. In the 1960s, DC motor became the core drive unit of industrial automation due to its characteristics of linear torque and superior speed regulation ability. After the negative feedback system is constructed by introducing tachogenerator generator and position encoder, high-precision speed and position control is realized, which dominates high-precision fields, such as CNC machine tools and military equipment. However, DC motors have fatal defects. First, the brush has short service life and high maintenance cost. Its commutation spark will produce electromagnetic interference. Second, it has poor environmental adaptability and low protection level, making it difficult to operate stably in harsh environments, which limits its application in textile, food processing, and other industries. AC motor has a broad application prospect because of its simple structure and brushless maintenance. From the early 1960s to the 1980s, due to limitations in speed regulation, frequency converters were introduced to achieve smooth speed regulation, but their lack of dynamic performance. After the 1980s, FOC technology emerged, which achieved fine control through decoupling, making the dynamic performance of AC motors comparable to that of DC motors, expanding its application and competitiveness. Meanwhile, direct torque technology is also a motor control technology worthy of attention. AC servo motors are divided into two categories according to their working principles. There are many AC permanent magnet synchronous servo motors, PMSM, used in small and medium power scenarios, which have the characteristics of high precision, small size, lightweight, high efficiency, and smooth operation. AC induction servo motor is used in asynchronous servo motor, high power scenarios, based on electromagnetic induction, and has large torque, strong overload capacity, good speed, regulation performance, and wide operating range. AC servo motors have many advantages, such as low maintenance cost, long service life, strong environmental adaptability, high precision, and fast response. It is widely used in many key fields to promote the development of industrial automation. After the technology accumulation and market precipitation over 10 years, China's servo motor industry has achieved a leap forward development. Under the increasingly fierce global competition, local brands have successfully broken the technological monopoly of foreign brands through continuous technological innovation and product iteration, and cultivated a number of leading companies that master core technologies. In the field of small and medium power applications, 0.75 to 7.5 kilowatts, domestic servo systems have occupied more than 65% of the market share due to their significant cost-effective advantages and have become the mainstream choice in the field of industrial automation. At present, the industry is accelerating breakthroughs in high power, greater than 15 kilowatts, high precision, plus or minus 0.01 degrees, and intelligent integration, promoting the in-depth development of domestic servo systems into high-end manufacturing. Next, let's focus on understanding the composition and working principle of AC permanent magnet synchronous servo motor. AC permanent magnet synchronous servo motor is mainly composed of stator, rotor, position or speed sensor, and servo driver. The stator is embedded with three-phase windings and generates rotating magnetic field when it's power on. The rotor is made of permanent magnet and interacts with the magnetic field of the stator to realize synchronous rotation. The position or speed sensor feeds back the rotor position and speed. The servo driver receives instructions and dynamically adjusts the current, ensuring magnetic field synchronization. The rotation control of AC permanent magnet synchronous servo motor mainly adopts the field-oriented control (FOC) method, which can accurately control the magnetic field magnitude and direction, enabling the motor torque to operate stably with low noise, high efficiency, and high-speed dynamic response capability. It is the best choice for high-efficiency control of AC permanent magnet synchronous motor at present. The following introduces the basic mathematical principles involved in FOC. The first is Clark transformation and inverse transformation. It is a mathematical tool for equivalent conversion of three-axis stationary coordinate system, ABC coordinate system, and two-axis stationary coordinate system, alpha-beta coordinate system. The core purpose is to simplify the analysis model of three-phase AC motor or power system and eliminate the redundancy of three-axis variables. The second is the Clark transformation, which is a mathematical transformation able to transform the vector in the stationary coordinate system, alpha-beta, into the rotating coordinate system, DQ, synchronously with the rotor. Next, let's introduce the principle of FOC control. The AC permanent magnet synchronous motor is composed of a stator and a rotor. The stator contains three-phase windings distributed symmetrically at 120 degrees. The rotor is composed of permanent magnets and a rotating shaft, and has a built-in position or speed sensor. After the three-phase winding is power on, three groups of electromagnetic fields are formed, which are equivalent to a single magnetic field vector after vector synthesis. When this vector is perpendicular Q-axis direction to the rotor magnetic field D-axis direction, it can generate the maximum torque. The space vector method can be used to abstract the three-phase current or voltage into the rotation vector, and the synthetic vector directly corresponds to the direction and intensity of stator magnetic field. FOC control detects the D-axis position of the rotor in real time and adjusts the three-phase current to make the stator magnetic field vector always perpendicular to the rotor magnetic field. It realizes motor steering and speed control by changing the direction, positive or negative, and amplitude of the vector in real time. The FOC feedback control process is as follows. First, sample the three-phase current of the motor, convert it into two-phase current through Clark transformation. Then perform Clark transformation according to the rotor position and decouple it into magnetic field and torque components. Then perform PID control on the magnetic field and torque components respectively to generate the adjustment voltage. Then obtain the stator equivalent voltage through inverse Clark transformation. Calculate the stator voltage of each phase through inverse Clark transformation, and finally generate the motor driving voltage through inverter in PWM signal. Through today's lesson, we've delved into the performance characteristics of AC permanent magnet synchronous servo motors, including high precision, low maintenance cost, strong environmental adaptability, and excellent dynamic performance. We've focused on the principle of FOC control, including Clark transformation, and current loop decoupling control. These technologies make the motor torque to operate stably with low noise, high efficiency, and fast dynamic response capability. That concludes this lesson. Thank you for listening. See you next time.